Feedback controllers are designed to generate a signal P that is sent to the final control element, which is usually a control valve. That signal P is computed based on the error of the controlled variable. That is, the difference between the set point for the controlled variable and its measured value. Like all real signals, the controller output will have maximum and minimum values, Pmin and Pmax. For what we call a reverse acting controller, the output signal P increases with increasing error signal E. This is called reverse acting because the error signal increases when the measured value decreases. Therefore, when the measured value of the controlled variable goes up, the controller output goes down, and that's why this is called a reverse acting controller. Because the controller output is computed by multiplying the controller gain by the error signal, a reverse acting controller has a positive controller gain, which is the slope of this line. A direct acting controller has the opposite behavior. For a direct acting controller, the output signal P decreases as the error signal increases. Therefore, direct acting controllers have a negative controller gain. It's important to pair the correct controller action with air to open or air to close valves to ensure that feedback control loops always provide what's called negative feedback. We want the controller to provide negative feedback so that the controller counteracts the behavior of the measured value of the controlled variable. If the measured value of the controlled variable is going up, then the error signal is going down. We want to be sure that the signal coming from the controller either opens or closes the final control element to bring the measured value of the controlled variable back to the set point. For that to happen, the entire feedback control loop must provide negative feedback. To ensure that the controller provides negative feedback, consider what happens at each element in a feedback control loop. Here we'll consider a composition controller on a blending tank. Assume that the composition analyzer transmitter has a signal that increases when the composition of the stream it's measuring increases. That is, the composition analyzer transmitter has a positive gain or is direct acting. The process also has a positive gain. That is, when the flow rate of stream 2 is increased, because stream 2 contains pure solute, the measured composition will also increase. So we can put a positive sign here for the process. Now suppose, due to process safety, we choose an air to close valve. The air to close valve has a negative gain. That is, when the signal coming into the valve increases, the manipulated variable, which is this flow rate, decreases. If the valve is air to close, then we can put a negative sign here representing the gain of the valve. In this case, we would want the controller to be direct acting. It should be direct acting because if the composition of the fluid in the tank begins to increase, the signal coming out of the transmitter will also increase, which will cause the error signal to go down. And as the error signal goes down, the controller output will go up. Increasing the controller output will cause the valve to close, which will counteract the effect of the increasing composition in the tank. Alternatively, if the composition of the solute in the tank is decreasing, then the signal at the transmitter will be going down. That reduction in the measured value will cause the error signal to go up. As the error signal goes up, the controller output will go down, which would open the air to close valve, allowing more of the solute to be added to the tank, and thereby restoring the composition closer to its set point. What controller action would we want if the valve instead were air to open? If the valve instead were air to open, then the sign at the control valve would be positive. In order for the control loop to provide negative feedback, we need an odd number of negative signs in the control loop, including the process, the analyzer transmitter, the controller, and the valve. You can consider additional alternatives, such as having the control valve on W1 instead of on W2, which might change the sign of one of the other elements of the control loop. To select the correct controller action, we need to know how the manipulated variable affects the controlled variable. In other words, what's the sign of the process gain? We also need to know the gains of all the other components of the control loop. We'll assume that sensors and transmitters have positive gains or are direct acting. The sign of the control valve gain should be determined based on process safety and other requirements. Only after knowing all of the other gains in the control loop can we select the correct gain for the controller. In Chapter 9 of the CBORD text, we described all of the elements of the control loop, which include sensor transmitters, controllers, actuators, and the process itself. The actuators are also called final control elements and are usually control valves. Understanding the behavior of all of these components of the control loop is important for the design of control systems. Most sensor transmitters have non-instantaneous dynamics, and most control valves, when they're installed, have some non-linearity in their behavior. So we talked about the design of control valves and pairing control valves with either direct acting or reverse acting controllers.